in this lecture we solve few more problems of transmission lines, but this time we are going to make use of the Smith chart to solve these transmission line problems. Let us take a problem of impedance measurement using a transmission line. As we have seen earlier, the measurement of complex impedance is very tedious at high frequencies because the measurement of phase is unreliable. So, the measurement of an unknown impedance at high frequencies is carried out by measuring the standing wave ratio and the location of the standing wave pattern, maximum or minimum. We calculate the unknown impedance. So, here is a setup, we are having a transmission line to which the unknown impedance is connected, and by using what is called a slotted transmission line, we measure the standing wave pattern on the transmission line. So, this is a variation of the voltage as a function of length on the transmission line. So, we measure the parameters. Let us say the maximum voltage which you see on the transmission line is 15 volts, the minimum voltage which we see is 5 volts. The location of the first maximum is 27 centimeters from the load end of the line, and the distance between the two adjacent maxima is 30 centimeter. Knowing this information now, we would like to find out what is the unknown impedance. First thing, since we know the distance between the two maxima of the standing wave pattern, this distance is lambda by 2, and that's the reason we have lambda by 2 equal to 30 centimeter. From here we can get the lambda which is 60 centimeter. Once we get the lambda, then the phase corresponding to this distance of 27 centimeter, 2 beta L, that is 2 into 2 pi by lambda into L, which is 27 centimeter, lambda is 60 centimeter. So, you get a phase 2 beta L which is 324 degrees. From the maximum and minimum voltage on the line, we can calculate the VSWR, and that is 15 by 5, that is equal to 3. Once we have this information, then we can go to the Smith chart to calculate the unknown impedance. So, we take the Smith chart, and since we know the VSWR, first we draw the VSWR circle on the Smith chart. So, what we do, we take the normalized R equal to 3 point on the horizontal axis on the right side of the center of the Smith chart and draw a circle passing through this. So, this circle is VSWR 3 circle. Then the rightmost point here, that represents the location of the voltage maximum, and the leftmost point on this circle shows the location of the voltage minimum. Since we know the location of the voltage maximum in our problem, we know this location on the transmission line, and now if I move from this voltage maximum points away from the generator by a distance of 27 centimeter, that is 324 degrees, then I must reach to the load point. So, essentially from the maximum location, if I move away from the generator, that means in the anti-clockwise direction by an angle of 324 degrees on this constant VSWR circle, whatever point I reach to, that point corresponds to the load impedance. So, I make a movement like this by 324 degrees, I reach to this point. Now, if I read off the value of the normalized resistance and reactance corresponding to this point, I get a value 1.15 minus j 1.23. So, the absolute impedance, if I multiply this by the characteristic impedance of the line, which is 50 ohms, then I get this normalized impedance multiplied by characteristic impedance, I get 57.5 minus j 61.5 ohms. So, the unknown impedance can be measured very easily without doing much complex calculations by using the Smith chart. Let us take now a problem for the quarter wave transformer. Again, we will consider a general problem here, that the impedance to be matched by using quarter wave transformer is not a real impedance. Let us say a load impedance of 75 minus j 35 ohms is to be matched to 50 ohms using quarter wave transformer. Design the matching setup. Now, if you recall, the quarter wave transformer basically can match two resistive impedances. Since our characteristic impedance is real, any real impedance can be matched to the characteristic impedance. However, the impedance which is given to us is a complex impedance, which is 75 minus j 35 ohms. So, by using a section of a transmission line, first we must transform this impedance to a real value. At that location, we insert a quarter wave transformer and we get a match. So, the setup essentially would be that this is the unknown impedance, which is 75 minus j 35 ohms. I introduce a section of a line of the same characteristic impedance. Let us say this is Z0 is 50 ohms. So, this line also is of characteristic impedance 50 ohms. Then the impedance transformed seen at this location should be real. So, at this location I can introduce a quarter wave transformer, I will get a match. So, now two things are to be found out in this problem. First is what should be this length and what should be the characteristic impedance of this quarter wave transformer. The length of the quarter wave transformer is lambda by 4. For finding out the impedance at this location, which will be real, and the length, we again make use of the Smith chart. So, first thing what we do, we take the Smith chart, mark the unknown impedance which is to be matched to 50 ohms. So, first we normalize this impedance of 75 minus j 35 ohms, mark this point on the Smith chart, draw a constant VSWR circle passing through this impedance. So, this circle is the constant VSWR circle corresponding to the load impedance 75 minus j 35. Now, as we move on this constant VSWR circle towards the generator, that means on the clockwise direction, if I move by a distance corresponding to AP, the impedance at this location seen will be real and it is the minimum resistance which we will see on the line. If I move by a distance corresponding to AQ in the clockwise direction, then I will reach to a location of voltage maximum and then the resistance seen at that location will be R max. So, there are two possibilities, either I insert a length of transmission line between the load and the quarter wave transformer by this, and then the impedance to be matched will correspond to this value, or I can take a distance corresponding to this and then the impedance to be matched will correspond to R max value. So, there are two solutions to these problems. Firstly, if I move by a distance AP and how I measure a distance, I take a radius vector, go to the circle here, here the lengths are marked on the outermost circle of the Smith chart. So, it starts from 0, then it goes all the way up to 0.25 and then goes up to 0.5. So, here the circumference is calibrated in terms of lambda. So, I can take a radius vector, read off this value, this is 0.306. If I move up to a point P which corresponds to 0.5 lambda, difference of these two will tell me the length of the line which is to be introduced between the load and the quarter wave transformer. So, one possible solution is that if I take this length, then that length will be 0.194 lambda and the impedance to be matched will be R min and that will be the 50 ohms multiplied by the normalized value here, which is 0.5. So now I get the impedance to be matched will be 25 ohms if I insert a length of a line between the load and the transformer of 0.194 lambda. Other possibility, if I go from A to Q, then the distance will be AQ will be 0.194, which is this distance, plus lambda by 4, 0.25. So that distance will be 0.444 lambda. So if I introduce a quarter wave transformer at a distance of 0.444 lambda from the load, then the impedance to be matched will be R max, and that will be 50 into normalized value 2 corresponding to this point Q. So if I take this as L in this case, then the impedance to be matched will be 25 ohms. So the characteristic impedance of the quarter wave transformer will be geometric mean of the characteristic impedance and the impedance to be matched, which is 25 ohms. So the characteristic impedance of the quarter wave transformer will be 35.35 ohms. On the other hand, if I take L as 0.444 lambda, then the resistance to be matched will be 100 ohms, and then the characteristic impedance of the quarter wave transformer would be geometric mean of 50 and 100, and that will be 70.7 ohms. So in this problem we see how to match a complex impedance to the characteristic impedance by using section of a transmission line and the quarter wave transformer. Let me remind you that initially the quarter wave transformer can match the impedances which are real. Only thing is, by using a section of a transmission line, we have converted a complex impedance into real impedance, and then we have used the concept of the quarter wave transformer. Let us take now one problem for the single stub matching. Let us say we are given an impedance of 90 minus j25 ohms. Now as we know that in a single stub matching, the line which are used for the matching purposes, the main line and the stub, they both have the same characteristic impedance, 50 ohms. So the parameter which are to be now calculated are the length of the transmission line L1, that gives the location where the stub is to be introduced on the main line, and the length of the stub Ls. So these two quantities are unknown. The impedance of the transmission line is same as the characteristic impedance of the line, which is 50 ohms. So as we proceed, first thing we do is we normalize this impedance with the characteristic impedance. So you get ZL normalized, that is this 90 minus j25 divided by 50. So this will be 1.8 minus j 0.5. Remember now that this is the impedance. The stub is connected in parallel with the main transmission line. So as we have seen earlier, whenever we have a parallel connection, the dealing with the admittances is more appropriate. So first our task would be to convert this impedance into admittance and then carry out the single stub matching in terms of admittances. So now we proceed as follows. Firstly, we consider the Smith chart as the impedance Smith chart. Since the impedance to be matched is 1.8 minus j 0.5, considering the chart as the impedance Smith chart, I mark this point ZL bar, which is 1.8 minus j 0.5. So this point here is the impedance to be matched. I draw a constant VSWR circle passing through this point. So this circle is the constant VSWR circle. Now, since we want to do the further calculations in admittances, first we convert this impedance to admittance. And as we have seen earlier, if I take a diagonally opposite point of ZL bar on this constant VSWR circle, then I get the normalized admittance at that location. So, this point, diagonally opposite point Q, gives me a normalized admittance corresponding to this normalized impedance. Let us say that normalized load admittance is GL plus JBL. So, essentially our single stub matching starts from here. This is the admittance which is to be matched by using a single stub matching where stub is connected in parallel with the main line. As we have seen in the single stub matching, the first is I move by a distance such that the resistive part of this admittance becomes unity. That means the conductance G1 that get transformed to the unity at this location. So, this point here, if I see, it should become some 1 plus J B 1. So, by moving along the main transmission line, first we set the conductive part to unity. Whatever is the susceptance part, that you cancel out by placing a stub in parallel with the main transmission line. So, here first we move on this constant VSWR circle up to a point where this constant VSWR circle intersects G equal to 1 circle, constant conductance G equal to 1 circle. So, this location here, this point now, which is given as R, this point is R. The admittance corresponding to this point is 1 plus JB1. How do I get the length or the location of this point? I just draw the radius vectors passing through these 2 points. That is the length which is L1 on the main transmission line. So, again I can read off the values of the length which are marked on the Smith chart. So, this location corresponds to 0.032 lambda, this is 0.152 lambda. I can get a length L1 which is 0.152 minus 0.032 is equal to 0.12 lambda. So, the location of the stub is 0.12 lambda from the load. Second thing you have to find out is the length of the stub, and for which this JB1 susceptance has to be cancelled. So, the stub has to introduce a susceptance of minus JB1. As we do, we take the mirror image of this point on the constant VSWR circle, find a constant susceptance circle passing through this point, take the outermost point on this circle. So, this point here T represents pure susceptance of a value minus JB1. So, now if I want to have a susceptance seen here minus JB1, from that susceptance if I go away from the generator till I reach to the short circuit point, then that gives me the length of the stub. So, from here this is my susceptance which I want to add. I have to move now away from the generator. So, I have to go in the anti-clockwise direction on this till I reach to the short circuit point. And since now this chart has become now the admittance chart, the point corresponding to the short circuit is the rightmost point. So, this is short circuit. So, I move on this in the anti-clockwise direction till I reach to the rightmost point on the Smith chart. So, again I can read the lengths. This point corresponds to 0.25 lambda, this is 0.402 lambda. So, the difference of these two, that gives me the length of the stub, and that is 0.402 minus 0.25 is equal to 0.152 lambda. So, now we have got the length of the stub, we have got the location of the stub. So, in a single stub matching, If the impedance is given first and if the line is connected in parallel with the stub, then the first step is to convert the impedance into admittance. Beyond that point, treat the chart as the admittance chart. Do the movement on the constant VSWR circle on the admittance chart. While calculating the length of the stub, remember, since the chart has become admittance chart, so the short circuit point is the rightmost point on the chart and the open circuit point is the leftmost point on the chart. So move on the chart from the reactance value which you want to match up to the short circuit point and you will get the length of the stub. So these are some of the problems which can be solved very easily with the help of the Smith chart. If I had to do the same calculation by using analytical approach, you will see finding the lengths and the locations of the stubs on the transmission line is extremely tedious task. So these examples clearly demonstrate the use of the Smith chart for solving complex transmission line problems. Having discussed down these problems, let me go to the final thing in the transmission line, that is the characteristic impedances for the various structures which you see in practice. At the beginning of this discussion on transmission line, we have seen various kinds of transmission lines like a coaxial line, parallel wire transmission line, microstrip structure and so on. In practice, then one would need to calculate the characteristic impedances of these lines. So let us see here directly the formulae which are used for the characteristic impedance of the various transmission lines. So the most commonly used transmission line is the coaxial line, which is practically used for making connections between any electronic equipment. So this structure is coaxial line, has a outer conductor which is cylindrical and an inner conductor. These are conductors and you apply a voltage between the center conductor and the outer conductor. Let us say the diameters of these two conductors are given by small d and capital D. And let us say the dielectric which is filling the medium between these two conductors is having a dielectric constant epsilon r, or the relative permittivity of the medium which is filling this cable is epsilon r. In practice, we use the material like perspex or Teflon for filling these cables. So the dielectric constant may lie typically in the range from 2 to 4. The characteristic impedance of this structure Z0 is equal to 138 divided by square root of epsilon r log of d by d. So the characteristic impedance for a coaxial line depends upon three things: the ratio of the inner and the outer diameter of the conductors and the dielectric constant of the medium filling the coaxial cable. If I now take some typical value just to calculate the impedance of that, just to get a feel what kind of parameters are required to realize certain characteristic impedances, let me take, just for simplicity, the epsilon r is equal to 4. So the Z0 for this coaxial cable will be 138 upon square root of 4 log of d upon d. So that is 69 log of d upon d. So, by inverting this relation, I can get the ratio d upon d is equal to 10 to the power z0 upon 69. What you see from this relation is that the ratio of d by d increases very rapidly as the characteristic impedance increases. Just when the Z0 is equal to 69 ohms, the ratio of the diameters of the outer and the inner conductor will be 10. When the impedance becomes double of 69, that time the ratio will become 100. So, the size of the outer conductor compared to the inner conductor increases very rapidly as the characteristic impedance of this line increases. What that means is that this structure, the coaxial structure, is more suited for realizing low characteristic impedances. And that is the reason typically the lines which are used in practice, the coaxial lines, their characteristic impedances are 50 ohms, 75 ohms, something like that. But if I say I want to realize a characteristic impedance of 200 ohms or 300 ohms, it will have a structure whose size will be physically prohibitive. We will not be able to realize the structure because the outer conductor size will become very large compared to the inner conductor. So, the coaxial structure intrinsically is more suited for realizing low characteristic impedances. So, typically we get the characteristic impedance for these lines which will be of the order of 50 ohms, 75 ohms and so on. Generally the cables are standardized for 50 ohms. However, whenever we go for the antenna applications, we get a cable which is having characteristic impedance 75 ohms. And the reason is that normally the antenna which is used in practice, we will see little later, that is half wave dipole, and its input impedance is very close to 75 ohms. So, just from the compatibility point of view of the impedances, whenever we use the cable for the antennas, we use the cable which is having a characteristic impedance 75 ohms. However, most of other applications or high frequency equipments, the impedance has been almost standardized to 50 ohms. Let us take the second line which is used very commonly in practice, and that is the parallel wire transmission line. As the name suggests, it has two conductors which are parallel. So, these are the conductors which are running parallel, and let us say that separation between these conductors center to center is given by d, and let us say the diameter of each conductor is given by small d. Generally these lines are used in air. Normally the open wire transmission line, you will see the parallel structure which are realized in air. So, the dielectric material which separates this conductor is generally air. However, there are certain applications where these are encapsulated inside some dielectric material. You may go and see this structure either whenever we are having a open wire like a power line or something, that is where you see this structure. You can also see this structure whenever you use the flat ribbon cable for connecting a Yagi antenna to TV. The flat ribbon cable which runs from the Yagi antenna to TV is essentially a parallel wire structure, and in that case there is no air medium, you are having a plastic encapsulation on that. So, there may be some kind of a encapsulation which will be on that, and then this will be filled with a dielectric material with some dielectric constant epsilon r. For this structure with general dielectric constant epsilon r, the characteristic impedance Z0 is 276 divided by square root of epsilon r log of 2d divided by d. As I mentioned, the dielectric separating this conductor normally is air, because normally this structure is realized as an open structure. So, epsilon r is generally 1. So, if I take epsilon r equal to 1, then Z0 will be 276 log of 2d upon d. One thing immediately one can notice is that the d I can make as small as d only. If I bring the two conductors to almost touch each other, then this quantity d will be equal to d. So, the minimum impedance which I can see on this line, if I use the dielectric as air, will be 276 log of 2, because d has become equal to d. Two conductors are almost touching each other. So, the minimum impedance which I can see for a open wire parallel wire transmission line will be 276 log of 2, so which will be about 0.3. So, if I take epsilon r is equal to 1, then Z0 will be 276 log of 2d upon d. So, for minimum d is equal to d, we get Z0 minimum, that is 276 log of 2, approximately 82.8 ohms. Just to take another value, if I take d by d equal to 5, I can substitute here d by d equal to 5, this becomes 10. So, log of 10 is 1. So, Z0 for this will be 276. So, as we can see, for this structure, realizing low impedance is more difficult. I cannot realize the impedances lower than 82.8 ohms. However, I can realize the high impedances rather easily. I can get, just by putting a d by d ratio of 5, I can realize the impedance of 276 ohms. And since I am talking about the two conductors which are parallel, separating these two conductors by a large amount is not that difficult. So, these lines intrinsically are capable of giving you the high characteristic impedances. These lines are also used in telephone lines. So, all the telephone line which you see on the towers, they are in the form of these parallel wire lines. So, generally the parallel wire transmission lines are used in those applications where you would like to realize high impedances, or if you use a parallel wire transmission line, conversely you have to deal with the high impedances. So, the two structures, the coaxial cable structure and the parallel wire structure, they are complementary in terms of characteristic impedance. The coaxial cable structure can give you low impedances rather easily, it is difficult to get high impedances, whereas if you go to the parallel wire line, then it is rather easier to realize the high characteristic impedance than the low characteristic impedance. So, typically for a parallel wire transmission line, the characteristic impedance would be like 300 ohms or 600 ohms. So, the lines which are standardized for the parallel wire lines, they have the characteristic impedance either 300 ohms or 600 ohms. The third structure which you see commonly in practice is what is called the microstrip line structure, and this structure normally is realized at the microwave frequencies for making circuits. Also, whenever we have a printed circuit board configurations, you have this kind of transmission lines. So, this structure is you have a dielectric slab whose dielectric constant is epsilon r, which is plated with a conductor on one side, and there is a strip of metal on the other side. The height of this dielectric slab is, let us say, h, and the width of this is, let us say, w. The characteristic impedance of this structure depends upon the dielectric constant and the ratio of w by h. So, the characteristic impedance for this line, what is called the microstrip line, is approximately given as 377 divided by square root of epsilon r Again, the dielectric which is used here can have a dielectric constant ranging from 2 to even 10, because when you go to microwave frequencies you can use the substrate which could be like alumina, for which the dielectric constant is 9.8 or something. So, in this configuration the dielectric constant values may have a very wide range, and also the W by H can vary by a very wide range. So, as we can see from here, you can realize a wide range of characteristic impedances, because if I use a high dielectric constant I can realize the low characteristic impedance. However, if I take a dielectric material whose dielectric constant is small, then the characteristic impedance can be increased. Also, by changing the ratio of W by H, the impedance can be varied by a large amount. But when we go to high frequencies, again we standardize the impedances either to 50 ohms if I am going to connect this structure to a coaxial cable, or I can realize the structure with higher impedances if I am going to make the connection to the parallel wire structure. There is a small difference, however, between these two connections, and that is, if I take a structure which is the coaxial cable structure, then the voltage is connected between the center conductor and the outer conductor, and the outer conductor is ground. So, I can have a voltage source which is connected to this between the center conductor and the outer conductor, which is the ground conductor. So, in a coaxial cable I have a center conductor to which the voltage is connected and the outer conductor is ground. Same is true for the microstrip line structure. This plane is a ground, so I can connect a voltage between this and the ground plane, again the same way as we did for the coaxial cable. So, this is the voltage is connected between this, and this point is ground. So, in both the cases the ground is defined and the voltage is applied with respect to ground. If I compare this structure, however, with the other structure which is the parallel wire transmission line structure, this structure is a completely floating structure. There is no ground defined for this structure. So, I can either say one of the conductor is at 0 potential and other one is at V, or I can say there is a virtual ground defined somewhere. With respect to that ground, this voltage is V by 2 plus this voltage is V by 2 minus. So, this structure is a floating structure for which the ground is not defined, whereas the other two structure, if you take, the ground is defined and the voltage is applied between the ground and the conductor. The other two structures are called then the unbalanced structure, and this structure is called the balanced structure. So, this structure, which is the parallel wire line, this structure is a balanced structure, whereas if I take a line which is a coaxial line or the microstrip line, then this structure is an unbalanced structure. So, in practice you see both kind of lines, the balanced lines and unbalanced lines, and whenever we make a connection between the balanced and unbalanced lines, two things are to be seen. One is of course the impedance has to be matched, so that there is no reflection from the junction. Second thing is, since we are making now a connection between the floating structure and a structure which is asymmetric or unbalanced, you require some transformer in between which can connect appropriately the voltages from a balanced structure to the unbalanced structure. This device is called balanced to unbalanced transformer, or in short it is called balun. So, a structure which matches the impedance as well as the nature of the cables is what is called balun, which is balanced to unbalanced structure. So, on this side essentially we have a structure which is the coaxial cable structure. So, I connect the outer conductor with this, the center conductor goes with that, and on the other side you have a balanced structure. So, you have a parallel wire line connected to this on the other side. You will see this balun whenever you make a connection between a Yagi antenna and a TV. That is the most practical application you can see around. Of course, there are many other high level technical applications where the balun is used, but practically whenever you are using a Yagi antenna for reception and connecting it to a TV, you bring the signal from the antenna by using that flat ribbon cable which I mentioned, that is a balanced structure. Then there is a small black box which is kept just at the input of the TV, because the connector which you are having on TV is a coaxial connector. So, that connector is a unbalanced connector. Also the impedance which you see here is 50 ohms, but the flat ribbon cable, that impedance is much different compared to the 50 ohms. So, normally we introduce a small box, what is called a balun, and which transform this impedance from the balanced structure to the unbalanced structure. If you do not do that, many times we get the reflections from the junctions which appears in the form of a ghost on the TV. So, appropriate transformation of the impedances on the line and also connecting balanced and unbalanced structure properly with the help of balun improves the quality of the reception of any high frequency signal. That essentially completes our discussion on the transmission line. Let me take a recap what we have done in this very important aspect of high frequency circuits, what is called transmission lines. We saw the limitation of the analysis of the lump circuit, and that is, as we go to the high frequencies, the size of the component becomes comparable to the wavelength, and then the voltages and currents cannot be assumed constant along any electronic component. So, we introduced the concept what is called a distributed element. We studied the effect what is called the transit time effect, and from there essentially we derived the relationship between voltage and current for high frequency circuits, that means for the circuits over which the transit time effects cannot be neglected, and we saw this relationship was in the form of differential equations. When we solve the differential equations, we got a solution of voltage and current which we saw were in the form of waves. So, in general we saw when we go to high frequencies, the voltages and currents exist in the form of waves on the electrical circuits. Then we studied the superposition of these waves, and we saw that in general there would be standing waves. We also investigated under what condition you will have two waves which are traveling in opposite directions, or you will have standing waves. So, we introduced the concept of what is called the reflection coefficient, which is a measure of energy reflected from the load. Then we introduced the concept of what is called the matching, which means if the load impedance is equal to the characteristic impedance, the energy is transformed from the generator to the load efficiently, and there is no reflection on the line. Following this, we studied the very important thing, which is the impedance transformation characteristics of the transmission lines, and then we went to many applications of transmission lines. So, we studied the application of transmission line as a circuit element, we studied the use of transmission line as resonant circuit, we studied the use of transmission line as stepping up voltage and current transformers, and then we studied the graphical approach to analyze the transmission line problems, that was the Smith chart. So, we also solved certain problems, and toward the end of this discussion on the transmission lines, we got the expression for the characteristic impedances for various structures which are used as transmission lines at high frequencies. So, we saw the coaxial cable, which is very common structure which is used at high frequencies, and we saw its characteristic impedance is rather low. It is difficult to realize high characteristic impedances by using the coaxial structure. On the contrary, the parallel wire structure is more capable of giving you the high characteristic impedances. We also saw certain applications where the coaxial and the parallel wire structure will be used. The third structure which we saw for transmission line was the microstrip line structure, which normally is seen at microwave frequencies of few gigahertz. Also, whenever we are having the transmission line on printed circuit boards, we see these transmission lines. So, we had a comparative discussion of these structures, and then we also saw very briefly how these different structures can be connected by using a device what is called baron. So, this gives now a overall picture of the transmission lines. Today, when even the computer speeds are going into gigahertz, the transmission line effects are going to play a very important role in circuit design. So, maybe few decades back, when the frequencies were not very high, the electronic circuit design was quite simple, because all these transmission line concepts were not playing any role in the electrical circuit. However, today when your chips are going to frequencies of few gigahertz, your computers are going to frequencies of few gigahertz, the reflections, the mismatching, all those things which we discussed have become very vital in making the electronic circuits. So, in today's electronic circuits, the concept of transmission line play a very, very important role. So, the subject of transmission line has become very important in recent years because of these high speed electronic circuits, which are now becoming part of our routine life.